Well, we're going to spend today, because I know how long it takes to do these questions, we're going to find center of mass. That's that guy. And first thing we're going to do is calculate the mass, which will be a double integral of some function. I'm going to call it f of xy, but actually it's very often called rho of xy, and that's called the density function. So I want you to think of the density function as being at any given point xy, how heavy is the material? So can you imagine if you made something out of different densities, right? So maybe a lot of lead at the beginning and a lot of aluminum at the end. Can you imagine someone being really clever and melding metals together? Going to be different densities. Sometimes you can do it by just making it different thicknesses, which has the same effect. And the mass then is the double integral of the density function. So if you wanted to just know how heavy does that lump of metal weigh, that double integral would do it. You then have to get a guy called the moments. And those are also double integrals of d. And they also contain the density function, which I'm calling f of xy. But they also contain one more term. What goes here where my finger is? So the moments around y. What goes here?
X. M.
X, and then y. And then you get x bar, which is where the m that I heard is coming from. And it is that guy, oops, over m. And y bar is that bar. Kind of have to, every time I see that, I have to give it a second look to make sure I haven't switched them around. Because you know how careless I am at the best of times, right? But I'm pretty sure that's the right way around. Because the way I remember it is, it's the opposite of what I would want it to be, right? So I would want that to say Y, and I would want this to say X. So that's how I kind of remember it, right? Because everyone's kind of back to front. Now, there is a lot of work in these questions. You can sometimes reduce your work if the density function is symmetric. So that means things like, x squared plus y squared over x plus y, right? If the density function is symmetric and the region D is symmetric. It's a little bit harder to describe what I mean by that, but can you imagine the region D is a square, right? That's symmetric, right? And can you imagine the region D was a whole circle, right? That would be symmetric, right? So in those kind of situations, and the circle doesn't need to be here, right? Whatever, forget that. If that happens, aren't those two guys going to be equal to each other? In which case you only need to find one of them and duplicate that with the other. Let me put some answers up here, or some questions where that happens, just so that we can see an example of it. Come on, find one for me. Yay, okay. If you want to see an example of what I'm talking about, question 8 is symmetric. So you only need to find one and you've got the other. Question 9 is symmetric. Okay, we're hitting the symmetrics now. Okay, so the last two questions, there's only 9 questions, right? But 8 and 9 are symmetric. Now, it might be that the question that you get, there might be another one that's symmetric and mine's wasn't, right? Because they changed the numbers a lot in these questions. Well, let's just jump right in head first and see the process from start to finish. I believe I finished off with question 3 last time, so I'm going to start with a version of 4. The density function, which is going to be the guy I call f of xy, is 9 lots of x plus y. Oh, by the way, that's symmetric. Oh, darn it, the answer isn't. Okay. And the region D is a triangle. And the triangle is there to there to there. So we have an origin, it's one of them, 2, 1, get you to here, 0, 3, get you to here, and then obviously back to where you started. So there's D. So this incorporates a whole load of stuff that we've done, right? Double integrals in particular. And I want to find this region D, and I have to set up the limits of integration for it. Now, we've seen triangles before. Sometimes you can go vertical, sometimes you can go also horizontal, right? You could do it both. And sometimes, and this is one of those sometimes, and this is looking deja vu again, but would you agree this one has to be done type 1 vertical? Because what you're going to go when you go vertical is that the y values are going to go from this straight line to that other straight line. If I try to do this horizontal, wouldn't it be only this line to the y-axis and then a totally different line to the y-axis? You see, it's not, you know, it's not one, it's not A and B, top and bottom. So that is a type 1, right? You have to do vertical. In this case, the x's then are going to be from 0 to 2. So if you imagine you're scanning it. So x is going to go 0 to 2. And then the y's, well, don't I basically need to find the equation of each of these lines? And won't this one be the big guy? And won't this one here be the small guy? So now we're changing tack for a little while, and we're now going to focus on finding the equation of lines. So this one here, this bottom one, passes through the origin, passes through the point 2, 1. If you do a little rise over run here, are you happy about y equals a half x? Right, so the equation of this line has a slope of a half and it goes through the origin. Are you comfortable with y equals a half x, or do I need to get into more detail? We're good, okay. And that's definitely the bottom, so that's the small guy that goes there. Now, this one here's got a lot more work in it, but if I do a rise over run, and would you agree it's 2 boxes by 2 boxes, so that makes the slope negative x, agreed? -1 pointing down the way. And since it has a y-intercept at 3, can't I just do that? Now, if I didn't want to do that, couldn't I do it the longer way? Find the slope and then do y minus y1 equals m brackets x minus x1, right? The point slope equation. And can you just trust me that that's what you would get? So even before we started the question, didn't we have some work to do? We had to figure out the limits of integration. So now we're going to do the mass, which is going to be the integral from x equals 0 to x equals 2, from y equals 1/2 x and to y equals negative x add 3, a density function of 9 lots of x add y, and I'm doing a dy here with the dx. Are you comfortable about the setup, limits of integration, all the bits and pieces? Not separable, got to do it the long way. So I'm going to do this guy first. I guess I should really call that 9x plus 9y. So let's pretend that I did that without having to write it all again. And so when you integrate with respect to y, you get 9xy plus 9 over 2 y squared. And then you evaluate it at 1/2 x, and you evaluate that at that point there. So far, so good. That's now going to be the integral from x equals 0 to x equals 2. And if you plug in this fella here, you get 9x negative x add 3 plus 9 over 2 negative x add 3 squared. Take away, add in a 1/2 x here, plus 9 over 2, 1/2 x squared dx. And you're going to trust me, but that's 54, according to what's in front of me. This is not hard. Isn't this just very time consuming, right? Because when you have to FOIL things and add things and combine things and do a power roll and, you know, la, 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 right? But can we just say, okay, I'll take your word for it, it's 54. I could do it myself if I needed to. That's fine. So we now move on to our next piece of the puzzle. So we're going to get m of y, and that's going to be the same double integral, essentially. Oops, the same double integral, which is this guy. So x equals 0 to x equals 2, y equals 1/2 x to y equals negative x add 3. Y times this guy. So if you introduce y times this guy, it's 9xy plus 9y squared dy dx. Are you happy about y times this guy, y times 9x, and y times that one, right?
Wouldn't it be x instead of y?
Yeah.
Oh. So let's check that out. This is going to be 9x squared, and this is going to be 9xy, right? So x equals 0, x equals 2, y equals 1/2 x, y equals negative x add 3. Since that's a y, it's going to be x times 9x plus 9y. And yep. I'm not sure how much of this you'd really need to write down because you're going to do your own version. There, 9x squared plus 9xy dy dx. So far, so good. And I'm going to cheat. It ends up being 81/2. What's that, about 5-10 minutes later? It ends up being 81/2. Be a little bit more careful with this one then. So the integral from 0 to 2, the integral from 1/2 x to negative x add 3, only this time it's going to be y times those guys. So it's going to be 0 to 2, 1/2 x, negative x add 3, and it would be 9xy plus 9y squared. And that again will take you a good 5-10 minutes. And again, I'm going to cheat. And this time answer is 81. So the center of mass is the moments around y divided by m. And the center of mass for the y coordinate is the moments around x with m. And so we have 81/2 divided by 54. That's X bar. And Y bar is 81 over 54. It's probably the only easy bit in this question. Do this one first, it looks easier. 81 divided by 54, and that gets me 3 upon 2. And this one here should get me 3/4, so let's find out if it does. 81 divided by 2 is that guy, divided by 54 is that guy. Yep, and it gets me 3/4. And so the center of mass is going to be at position 3/4, 3/2. Now I'll look at my shape and I'll try and best I can plot the point 3/4, 3/2. Okay, 3/4. Well, that's probably where my green one is, and 3/2 is there. So there. Does that look reasonable? It is kind of in the middle of the shape. Bear in mind that the shape's density changes depending on its position. Right. So before we move on to our next question, let's talk about center of mass and weird things that can happen with center of
Can I
mass.
see the other paper real quick?
Sure. There we go. If the density function is a fixed number, right? So we're talking about it's the same weight no matter where you are in the plate. It wouldn't surprise you that the center of mass would be right there. Agreed? If your shape was only the top half of a circle, the center of the mass would be about here. All I can tell you for sure is that the x coordinate would be 0. Does that seem reasonable? Based on just symmetry. So we're assuming that all of these functions have a fixed density function, right? They weigh the same everywhere, right? If they don't, then all bets are off. Suppose my shape looked like a donut. Where would the center of mass be in this object?
And still be in the exact center.
Isn't that an example of a shape whose center of mass is not inside the region? It is possible for centers of mass not to be in the surface, right? It seems, well, maybe it isn't unusual looking at that, but it is possible. It is also possible to have a triangle that might look something like this and end up with a center of mass down here. Now, the only way that would happen would be if the density function was involved. So if you had a shape where it's maybe very dense at the bottom and then less dense towards the outside, you could have a situation where the center of mass is not inside the shape. Now, if you are a person who's building things, construction engineer, civil engineer, knowing where the center of mass of your shape is very important. I have seen buildings that deliberately, and I'm exaggerating them, look like that. Have you seen, but I'm exaggerating this a little bit. Architects love doing stupid things, right? Now, if they are sensible about it, the center of the mass would probably be there, right? If you're being clever about things. But if you're being not so clever about things, couldn't the center of mass be outside the building? Isn't that going to put a lot of strain structurally on that building through time? And if you get a really strong wind that just happens to point or blow in a direction that is encouraging the fall over, won't you get a possibility of structural defects? So when you build things, if you ever become an architect or a civil engineer, you really do want to find the center of mass of things, because they very often give you a stability thing. I am now going to do my last one and move on here. I cannot draw to save myself. Have you ever seen container ships that look like that? Exaggeration again, right? If you have a container ship that has got a lot of stuff on it and you stack it badly, or you stack it so too much heavy stuff, couldn't you get the center of mass not there, which is kind of where you want it to be, but here? Now, what that will make that ship do is dig into the sea. So as it is traveling, it will go bow in, right? So you can imagine a ship that's always jumping into, cutting into the water. And lots of reason why it's a bad idea. Isn't that going to make it much less fuel efficient, right? It'll take more gas to move forward. It'll probably slow you down. But in a storm, isn't that likely? If you go too far into the water, couldn't you start taking on water and sink? So you don't want people who stack container ships. I've seen container ships on TV, and it's a miracle to me that they work. Have you ever seen them? They're like, wow, how does that thing not keel over, for starters, right? I assume that they're very clever about it. I mean, if I was doing it, wouldn't you put heavy guys on the bottom and light guys on the top? Wouldn't that be one way of keeping the center of mass low? Because you don't want the center of mass high either. Because if it's high, doesn't that give you, you know, that instability, right? You could keel over on your side, which is not good. So, trying to sell you center of mass are good things to get. Center of masses are a pain to do. Great. There are a lot of work in them. And we got time for, yeah, time for at least one, if not two more. Now, let me check. I want to see if I've got a circle one I can do instead. Oh, let's do a symmetry one. Yeah. I promised you 8 and 9 are symmetry. So let's show you what that looks like. We have a circle. Now, why is that symmetric? Oh, let me skip that one. I might come back to the one as my second choice. Let's do this one. Find the center of mass of a shape that is an isosceles right triangle with equal sides of length A. See figure below. Oh, okay. A and A. Okay. And the density function for any given point x, y is described as proportional to the square of the distance from the vertex opposite the hypotenuse. Well, why couldn't you just say it's the square of that distance there? So if you imagine this point here as being xy, then that distance there squared. Right, well, the distance from there to there is the square root of x squared plus y squared. And if you square it, you do that. And since it's proportional to it, you do that, which means it's k x squared plus y squared. So evidently this one is, I wouldn't call that symmetric, but anyway, in this question, x bar is going to be y bar. Is there any? No, there's no clues there. Okay. So the mass is going to be the double integral of my density function, dA. And I am going to do this one is a type 1. I'm going to do vertical. So that means the x's are going to go from 0 to a, and the y's are going to go from 0 to the equation of this straight line. Ah, that's interesting. If you look at rise and run, isn't this negative x? Isn't it -1 as a slope? Because it's a over a. And since it passes through the y-axis, it's negative x add a. So the mass is going to be the integral from x equals 0 to x equals a. And then it's going to be from y equals 0 to y equals negative x add a. And then we're going to put in the density function, which is that guy. And then we're going to do a dy. And then we're going to do a dx. And I'm going to treat a like it was 42, because it is, it's just a constant. So it's going to be the integral from 0 to a. If you call that kx squared and you call that ky squared, you get kx squared plus ky squared, right? And now I need to integrate them. So that's going to be kx squared y plus k over 3y cubed, evaluated at y equals 0 and y equals negative x add a. So k times x squared with a y, k times y squared integrated with a y. We now have x equals 0 to x equals a. And if you plug in this fella, you get kx squared negative x add a. And if you plug it in here, you get k thirds negative x add a cubed. Take away a whole load of nothings. Oh, I was hoping they would tell me what that was equal to so I could cheat and just say it's equal to, but they don't, the little darlings. Can I ask it to tell me what they are? Yeah, okay. I have to do a different kind of cheat here. And you are going to trust me that that's what you eventually get, because that's what they tell me. Now, they say by symmetry, so that's fine. So it is symmetric. So I'm only going to find that guy. So it's going to be the integral from x equals 0 to x equals a, the integral from y equals 0 to y equals negative x add a. And to get this fella, you multiply this expression with an x. So it's going to be kx cubed plus ky squared x dy dx. And if you do all of that guy, you get 1/15 k e to the 5. And you're just going to have to trust me, but that's what you get. And so x bar is the moments around y divided by the mass, which is 1/15 k e to the 5 divided by 1/6 k e to the 4, and an awful lot of cancelling, and you end up with simply 2/5 of a. And because of symmetry, so is the y guy. So the centre mass of this shape is basically that guy. I know I've done a lot of cheating here, but really this is just a mess. I mean, it's not hard to do. It's just a whole load of foiling. I mean, look at that. Wouldn't you have to find negative x add a cubed, right? I mean, it's not hard to do. And what would it be? Negative x cubed minus 3x squared a minus 3, oh, plus 3xa squared plus an a cubed. I mean, it's doable, but ridiculously ugly. And where would that go? Curious. So evidently you only go 2/5. So if you imagine that's a and a half a is here and a half a is about here, you go, I'm really good at picking things by coincidence, you go roughly about there. Okay, it's not directly obvious that that's what you get, but that's what you're going to deal with. So we have time to do one more. Okay, I'm not going to cheat with the last one. I will just do the whole thing. Seems only fair. So we are given, they call it lamina, right? And basically we're given x squared plus y squared less than or equal to 36. But we're only interested in the first quadrant. So that's what D looks like. Whenever you see a circle or a part of a circle, shouldn't you be thinking polar? So I'm going to think polar. And R and theta are the go-to guys, right, when it's polar. Great. Okay. Based on this quarter circle, what would the range in R be? How would you describe this in terms of the range of R values?
0,
Yeah.
6.
Agreed. And again, what would you describe it in terms of the range of thetas?
From 0 to pi over 2.
You all comfortable about that? Now, they have a density function. And in question 8, the density function is described as any point it's proportional to the square of its distance from the origin. We just did that, you know, the square of the distance from the origin. And didn't it end up being k because proportional? And the square of the distance is that. Now, in terms of polar, doesn't that become k r squared? Are you comfortable? So our mass is going to be the integral from theta equals 0 to theta equals pi upon 2. And then it's going to go from r equals 0 to r equals 6. And then the density function, which is that guy, times r dr d theta. Don't forget that r. You know, when you go polar, you get an extra r. So this is now going to be from 0 to pi upon 2, from 0 to 6 of kr cubed dr d theta. Is this one separable? Can I do a separation on this one?
Yes.
And just because I want to, I'm going to separate it this way. This guy is going to get the k. And this guy here is going to get the r cubed. Are you comfortable that since k is a constant, you could give it to either of them? If I decided to call this k r cubed, wouldn't I have to call this 1? Right. I just decided that's the order I'm going to do it. If you do this one, you will eventually get pi upon 2k. If you do this one, you'll get 1/4 r to the 4, evaluated at 0 and at 6. And that's not nice. So let's do it. 6 to the power of 4, which is that guy, divided by 4 is that guy, and I get 324. Take away nothing, which gets me 162 pi k, which is actually not that bad. So we're comfortable out the mass ends up being this. Limits of integration, the density function is proportional, that's what the key part is, to the square of the distance to the origin, which gave me this. So as we're doing this one all the way to the end. Oh, by the way, it's symmetric. So I only need to do it once in duplicate. So this guy is going to be the integral from theta equals 0 to theta equals pi upon 2, from r equals 0 to r equals 6. And we already know the density function and the r value, but let's pretend we didn't. It's going to be x times kr squared times r dr d theta. And since I'm working in polar format, I need to replace any x and y's that are left over, in this case just an x, with an r cos theta. And I'll join these guys together and get kr cubed dr d theta. That in turn is now going to go theta equals 0 to pi upon 2, r equals 0 to 6. And we now have k r to the 4 cosine theta dr d theta. Is this one separable? Can I do that as two single integrals? So let's do it then. This is cosmetic. This guy definitely has r to the 4 in it. And this guy definitely has cosine of theta in it. Here's the cosmetic bit. Who do I give the k to?
Wherever you want.
Yeah, wherever you want. Cosmetically then, which one do you think just looks nicer?
R.
You have no taste whatsoever. That is much prettier to me than where you wanted to put it. But is it the answer? Just like you said, it don't matter, right? It really doesn't. I just think it looks prettier there. Now, if you do this guy, you get k sine theta evaluated at 0 and at pi upon 2. And if you do this fella, you get a power rule, which is this fella, evaluated at 0 and at 6. This guy gets you k times the sine of pi upon 2, take away k times the sine of 0. And this guy just gets you 1/5, 6 to the power of 5, take away nothing. So 6 to the power of 5 is 7776. So 7776 fifths. And the sine of pi upon 2 is 1. And k times 1 is k, and that's nothing, so you just get a k. So the moment around y is 7776 over 5k. And I had a quick look, and it's right. So x bar is the moments around y divided by m. And so it's 7776 5k all over 1 162 pi k. Oh, God in Himmel, the k's cancel. There's going to be a pi on the bottom, but I've basically got this guy over this guy, and I need to figure out what they simplify as. I think this might put a strain on the calculator, but here goes. Put a bracket just for safety. 7776 divided by 5, divided by 162 on the bottom. And I get 9.6, which if I turn that into a fraction, I get 48 fifths, and the pi is still there. And it is correct. And since it's symmetric, you get that guy for free. So there's your center of mass. I don't know where that is. I'd have to figure it out as a decimal, but if I was a guessing person, would it seem reasonable to be somewhere like that, maybe? Maybe a little bit further up. Do we have any questions? Okay, for the last few moments, I'm going to just do a quick talk through the rest of these questions. While I'm doing that, why don't you put your last name down for attendance? Right, there we go. Okay, if you're doing question 5, y equals 1 minus x squared and y equals 0, won't they describe the boundary? So aren't you going to either do a vertical or a horizontal? My best guess is that that's going to be a type 1, right? A vertical rectangle deal. And it is going to be downright ugly. It's not going to come out pretty. In this one here, you're going to do essentially putting all of this together to get the region. And now that I've seen that one, I'm going to nip back to that in a minute and kind of put it in to show you what it looks like, because there's an awful lot of information going into that one. Right. Isn't question 7 basically very similar to the one we did before? They just kind of take you through it slowly. But the key here is, when you see that, isn't that a clue that you should go polar? Right? If your region, right, your D has anything to do with a circle, which means if you ever see x squared plus y squared, you know, greater than, less than, whatever, you're talking circles. And we've done 8 and 9. So the last guy, and we're finished, is this guy. Now, Desmos is your friend. If you do e to the negative x, what does that look like? That looks like this. What does y equals 0 look like? What is it the same thing as?
The x-axis.
Okay, so bounded along here. X equals 0, isn't that the y-axis? It's bounded here. And x equals 3 is here. When you put that package together, can you see the guy we're talking about? Right, that is D. If you want to set that guy up, would you agree that a type 1, a vertical rectangle, is the way to go? And x is going to go 0 and 3. And the y is simply just going to be from 0 to the curve, which is e to the x. When you do this one, when you find my, right, the moment about the y's, you're going to have to integrate somewhere along the line, you're going to have to integrate an x e to the x. I can't imagine it being avoided. If you integrate an x e to the x, aren't you going to have to do an integration by parts? So just be on the lookout for, not all integrations are easy to do, they're just big and boring. Some of them are quite small to do, but you have to do some work, right? Like an integration by parts. I don't think, looking at what I can see in front of me, that there are any substitutions. Go figure. Wasn't yesterday everything in their mother was a U-sub? Here it's just polynomials, and it looks like you're going to have one integration by parts. Yeah.
I thought you could integrate by parts. So the y should equal e to the negative x, and I thought you could take that and use sub.
Oh, okay, that should be negative x. It's still going to be integration by parts. I'm pretty
Okay.
sure that one of the guys that you're going to integrate is going to look like that. Right, that'll be a piece of the puzzle. And what I'm getting at is, won't that be an integration by parts?
All right,
Right.
I understand it.
That's what I'm saying. Well, that is us for today. I'll hang about for any questions. I don't think I can really say we learned some cool stuff today. I can say we learned some boring stuff today. I can certainly say that. And we learned how to do really long questions today. But that's about all I can say, honestly. So see you tomorrow. Bye-bye.